Hey everyone, this is Josh Myers and I am bringing you a skill building video on electron configuration on behalf of Academia on Demand. Okay, so in the last video where we talked about molecular orbital theory, we discussed the idea of representing the electron, what we call the electron configuration of an element using the boxes and the arrows. And what we will be doing in this video is we will be simply furthering this concept by making it simpler, by making this visual idea slightly simpler. So then anytime that we want to talk about the number of electrons that any element has on the periodic table, we can do so. We can represent it in a very clear, fluent way that all chemistry people can understand. It's a way of communication. It's our language of chemistry. Okay, so as we know, I have gotten rid of this periodic table that we have had for the last couple of videos. However, one thing I would like to show you guys first, and this is going to look a little bit like a homemade movie, but this is what I'm going to do. I am going to put the periodic table in front of the camera so we can see it. And the first thing that we are seeing here is the idea that the group 1 and group 2 groups, group 1 and group 2 are represented by the S sublevel, meaning that their electrons are in the S sublevel. And now, as we know, as we've seen, the group 3 to what we call 0 or 8 is represented by the P sublevel. Those electrons are in the P orbitals. And then finally, one thing now that we haven't talked about is these transition metals, the ones in the middle that connect the alkali metals and the alkaline earth metals to the nonmetals over here. The things in the middle, the transition metals is what we call them. They are represented by the D sublevel. And now finally, if we want to be completely clear on exactly all of this orbital stuff, there is this series at the bottom, and they are called the lanthanide and the actinide series. And exactly what they are is that they are elements that have been synthesized through unnatural means. They are not found in nature, but they have simply been made by our crazy human ability to make science and make things happen. And they are represented by the F sublevel. The F sublevel. And if you are ever asked to name any of them, they will be easily nameable using the F sublevel. Okay, so what we are going to do today is we are going to first relate what we talked about in the last video regarding the box and arrow method, and we will relate this to a simpler method of expressing this electron configuration idea, and then we will do some practice problems. Okay, so let's see which element should I do the box and arrow electron configuration of. Okay, let's do sulfur. Sulfur. And this pen is still failing me. Maybe I shall switch it. Yes, I am going to switch it. It is bothering me too much. Okay. Alright, let's erase this. I know this seems like a very unprofessional thing to do, but I have to show you that I am human too. I make mistakes. My markers make mistakes too. Okay, so sulfur. And it is located in the third energy level, and it looks like it has, so third energy level, and it looks like it has 4 electrons in its outermost P sublevel. 4 electrons in 3p. Okay. So now, as we know from before, the orbitals, the sublevels themselves, can be divided in terms of the amount of energy that they represent. And so this arrow represents that when we do our box arrow diagrams, that the energy of different orbitals is different, and thus this makes it such that we fill the lower energy orbitals first. So the lowest energy orbital is the 1s orbital, and so as we know, the orbital itself is represented by a box. And then because we know an orbital contains a maximum of 2 electrons, these first 2 electrons will fill the orbital, and they are represented by arrows that point in opposite directions, and this is representative of spin. And anytime that an orbital is filled, the electrons must be spinning in opposite directions. Again, quantum physics is pretty nuts, but that is what quantum physics deems to be we call most energetically favorable. And now I'm filling the 2s orbital. And after I filled the 2s orbital, we now move to the 2p orbital. The 2p orbital, and we are simply moving across the periodic table now. Okay, so 2p sublevel represented by 3 orbitals. Okay, 2p. And so now we know that sulfur is in the 3rd energy level, so therefore every electron that should be present in the 2p orbital, the 2p orbital is completely filled, so there should be 6 electrons in this 2p orbital. Now we are moving to the 3rd energy level. So then 3s, the 3s energy orbital is the one box, again, with 1 arrow up, 1 arrow down. Now 3p, and this is the one it ends that the outermost electrons are contained in. So we have to be careful here now. We cannot simply fill up these boxes. We have to use our brains and think. Okay, 3p. And as we've seen, sulfur is in group 6, which means that it has 4 electrons in the 3p orbital. Because as we know, the p orbital, p sublevel, now I'm almost using these terms synonymously, are represented by the groups between the groups 3 and 0 or 8. And so therefore 6 is 1, 2, 3, 4. So therefore there are 4 electrons in this 3p sublevel. And as we know, Hud's rule, we must half fill all of the electrons, all of the orbitals with 1 electron before we can fill them with 2. And this, again, this idea of energetic stability. Okay, so there we have it. That is the electron configuration of sulfur. And so now you are asking, what is this easier way, Josh? How can we represent this idea of where all the electrons are, this idea that is of electron configuration in a simpler manner? And I'm going to tell you what we do is we can make these boxes and arrow numbers. So if we take this down here, if we take our 1s orbital down here, we know that it's got 2 electrons in it. And so what we can do is we can call it 1s2, or what I would say 1s squared, but it's easier to use 2 in this sense. Let's say 1s2. And the next one, it is also completely filled. There's the 2s orbital, so we are going to call it 2s2. Okay, the third set of sublevels here, the 2p sublevel, and it has 6 electrons on it. It is filled, so it is 2p6. 2p6, and now 3s, and now this is very predictable, 3s2, and finally this last orbital, this last 3p sublevel is 3p4, because there are 4 electrons in it. And so if we put this together in an expression, we would say the electron configuration of sulfur. So sulfur, the electron configuration of sulfur is 1s2, 2s2, 2p6, 3s2, and then finally 3p4. And so now we've taken this big picture, this idea of the energies increasing as we move along the orbitals. These energies increasing, we've put it in this small expression right here. Look at how much easier that is. And so really all this means so far is that as we move across the periodic table, we add another electron. and it simply goes into either an S or a P orbital or sublevel. And now what I'm going to do is I'm going to expand your understanding of exactly what all of this energy orbital stuff means. Okay, so this blue marker is a lot harder to erase, and I don't know why, but it is causing me lots of difficulties right now. It's causing me lots of difficulties. Okay, so let's keep trying. All we can do is keep trying ever in life. Okay, so that is enough, I think. I think you can see perfectly fine. Okay, so what I have alluded to in this previous discussion I've just had is the idea that this progression of S and P orbitals may not be as simple as this once we get into what we call the D sublevel and the F sublevel. So if we look back at our periodic table, we can see that we have S and then we have our P. But then when we go down to 4S, the 4S sublevel, now we go into the D sublevels. But the difference is that the D sublevel starts at 3D. Okay, so let's make this simple rule, and you'll always remember it till the end of time as you first saw it here. Okay, so if we start and we say the first energy level, second energy level, third energy level, the fourth energy level, then finally the fifth energy level. And let's list out all of the orbitals, all of the sub-level orbitals that are filled. So if we have 1s, then we have 2s and 2p. And so this, as we know, as we go up one energy level, there is another orbital added, or another sub-level added. So as we know then that it's 3s, and there's a 3p sublevel, and there's also a 3d sublevel. And this is starting to get into unknown territory now. 4s, let's make a sixth one actually. 4s, 4p, and 4d, and then 4f, the 4f sublevel. And now 5s, and you guys now get the point. 5p, 5d, 5f. And if we were to now talk about something, we would say the next sublevel would be 5G, but fortunately there's no elements left that would fit into this 5G. But hypothetically speaking, there exists a 5G orbital. Okay, so now how does this memory trick work? Because what this memory trick is, what I've been doing is I've been setting up for a memory trick that allows us to always remember the energies of the orbitals relative to each other. Okay, and so what we can do, did I just move you? I think you can see, okay. And what we can do here is that we have a situation where we can say that you draw an arrow this way, it only goes through 1s. You draw an arrow this way, now it only goes through 2s. But now if you go to the next element, 2p, you draw an arrow this way, it goes through 2p and 3s. And so this represents the progression of the energies, the relative energies from lowest to highest of the sublevels. So 1s is first, 2s is second, 2p is third, and then 3s. But now if we draw this line this way, now it's 3p, and then we skipped 3d and went to 4s. And now this is starting to make sense. Now this is starting to make sense of why this is significant, because it's tricky. You can't just say 3p and then 3d. Their 4s is of lower energy than 3d is. And then if you draw your 3d orbital, it's going to go 3d, 4p, and then 5s. And that is how the energy progression goes in this sort of world of chemistry. It is simply how it works, is that this line diagram will always, forever and ever, represent the relative energies of all of these sublevels. And so now now that I only have limited amount of time left in this video, let's do a couple of quick examples. So let's do chromium, and chromium has 4 electrons, so chromium has 4 electrons in the 3D sublevel. So if we were talking about the electron configuration of chromium, we would say that it is 1s2, 2s2, because now we are just filling the sublevels. We would say 2p6, and then we would say 3. We would say 3s2, 3p6, and then 4s2, and then finally we would go 3d4. Now this is a special case. This is a special case where in fact an electron is the position of the electron is changed. Because as we know from Hut's rule, or an implication of Hut's rule, is that all orbitals are more stable when they are half filled. And what this means is that here we have 10 d block elements and 5 orbitals, which means that 4 of the 5 are half filled right now. And so chromium, as a part of the physical world, says to itself, wouldn't it be great, wouldn't it be just dandy if I could half fill all of my d orbitals? And this is exactly how it works. It works for energetic stability. And the most energetically stable state here is to have a state in which there is a half-filled s orbital and then 5 half-filled d orbitals. And now we are seeing why this can get confusing. And now in the next video, we will do some more examples. Now that we've gotten through all this crazy stuff on exactly why this works the way it does, we are going to simply just get right to the story of a lot of different electron configurations and look at a little bit more about how it works now that we've understood why it is the way it is. See you guys.